next speaker will be Shifra Mandel. She's an NSF fellow at Columbia University. Her prior work includes high-energy observational X-ray studies of a variety of objects in our galaxy, with a particular focus on accreting compact objects in the galactic center. And today she will talk about the black hole extra binary MAXI J1744, which is in our galactic center and has been pretty active in the last couple of months. And please take it away.
Thank you. Galactic Center is a weird and wonderful place full of exotic objects. You've got your supermassive black hole, Sgr A. You've got super dense young star clusters, supernova remnants, and of course, more X-ray binaries than we can find in any other part of the galaxy. This includes a remarkably high number of X-ray transients. You can see many of them in this swift image of the central 20 arc minutes of the galaxy. And when you zoom into the central 2 arc minutes for Chandra, then you see even more X-ray transients pop up. However, this is nothing compared to the central parsec of the galaxy, where you can find another 8 X-ray transients, not including Sgr or the PWNG. 5.9. So as you can see, this is a very dense and dynamic environment that is regularly monitored by X-ray telescopes. And on average, we've seen a new X-ray transient every couple of years pop up in this region. In 2016, actually, we had 2 new outbursts. We had this source right here and this one here popping up to the north and south of Sgr. So that was a really great year for us. But then nothing, a dry spell, radio silence or X-ray silence, as the case may be, that lasted for 9 years until finally, boom, MAXI detected this bright new transient on January 2nd of this year. MAXI J1744-294. It's the brightest transient that's ever been observed in the central parsec. And it's located only 18 arc seconds away from Sgr. That's less than a parsec at the galactic center distance. So as you can imagine, we're really excited about this. And we launched an extended observing campaign to monitor this outburst, not just with every major X-ray observatory out there, but also with multi-wavelength observations, including MeerKAT in the radio band and Keck in the near infrared. And we've assembled a fantastic team to collaborate on the vast amounts of data that we gathered. Unfortunately, I don't have time to go through all the names, but a lot of incredible researchers working on this study. Before I dive into the analysis of the source, just a quick review of the high energy emission of low mass X-ray binaries, LMXBs, which we believe this source is. So as you know, LMXBs consist of a compact object that's accreting from a low mass donor star. They tend to undergo occasional outbursts when they brighten by many orders of magnitude. And there are several different X-ray emission processes that can occur throughout the outburst. You have thermal emission coming from the accretion disk, where the temperature increases towards the inner edge. Then you have non-thermal emission from inverse Compton scattering, where some of these thermal disk photons get upscattered by this corona, this cloud of hot electrons around the compact object. And finally, you get some reflection, which is when Comptonized photons are bounced back onto the disk, which manifests in emission lines, as well as the characteristic Compton reflection hump. So let's dive in and take a look at what the spectrum from MAXI J1744 looks like. So here I have an example from an observation that was done jointly with NuSTAR, XMM, and XRISM back in March. And you can see the outline of the thermal disk emission here. And the hard Comptonized tail to the right over here. And then we have, in this particular case, a very narrow iron emission line right here above this blue arrow. The spectra varied considerably throughout the outburst, but these are the main components that, for the most part, were present with different strengths. So I'm going to focus in for a moment on the iron emission line. So as I mentioned, this was a very special observation because we got simultaneous data, not just with NuSTAR and XMM, but also with XRISM. So the XRISM analysis is being led by MAXI J at University, and we are preparing to publish these results by the end of next week. So keep a lookout for that. Now, as you can see from the XRISM spectrum, there's a lot of iron 25 emission. Although not all of it is from MAXI J1744, we of course have also diffuse iron 25 from the Galactic Center region, including from the supernova remnant Sgr A East. There are also a lot of unresolved CVs in the central arc minutes. And XRISM has exquisite spectral resolution, but not great angular resolution. And so there's a lot of contamination here that we had to model, including from a nearby neutron star LMXB. So we had to do a lot of detailed modeling of those different components, but after cleaning it up, we see definitely some very strong iron 25 emission or helium-like iron after subtracting all the different sources of contamination. So this is what is, we believe is truly intrinsic to our source, MAXI J1744. Now, interestingly, after fitting the known iron K alpha emission lines, we still see some very significant residuals in the XRISM spectrum that indicates that there are additional lines. We do not know what they are. They don't match any known atomic lines that we know about. But if anyone here has any ideas, please do come talk to me because we would love to hear them. As I mentioned before, we have a lot of data for this source, including from SWIFT, which monitors the Galactic Center almost every day. And I was able to put together these detailed light curves showing the evolution of the outburst from February onwards. And the observations, in fact, are still ongoing. So this will be updated. Now, the plot here on the left is called a hardness intensity diagram, or HID, and it's meant to show how the spectral hardness changes with flux over time. MAXI J1744 was first detected in January, but we don't actually know when it outbursted because the Galactic Center was not visible before it was detected. And when SWIFT started monitoring it, the outburst was already in the bright soft state. As many of you know, X-ray transients typically start out in the low hard state, and then they get brighter and softer. But it was already in the soft state when it was first detected, and it continued to get brighter all the way through August. And then the flux started to decline, but initially the spectrum still stayed soft, which you can see here as the count rate declined, you still had a pretty soft hardness ratio until July when it actually finally entered the hard state. So of course, SWIFT has a fairly limited bandpass. So let's take a look at what NuSTAR observed. So NuSTAR, of course, has a bandpass that extends to 79 keV. So here on the right, I have a hardness intensity diagram where the hard band is defined as a 10 to 50 keV range, and the soft band is 2 to 10 keV. And just note that the two HIDs are not equivalent to each other, not just because their energy bands are different, but also the NuSTAR HID uses flux units, whereas the SWIFT one uses count rate. That's because it's really challenging to constrain the SWIFT spectrum just in that narrow band. And once again, you can see that the source was quite soft in February when it was first detected. So right about here, February and March, it's soft. It becomes brighter, very slightly harder in April, and then becomes much fainter as the months go by, but it doesn't harden until pretty recently, actually. So this follows what we call the characteristic hue diagram for X-ray transients, where they start out low and hard, they become bright and soft, and then they decline again to the low hard state. So as I mentioned before, the spectrum changed significantly over the course of the outburst. You can see it here if you look at the iron lines in these residual plots. So this is a subset of the NuSTAR observations. And over the course of just a few days, and in one case on April 7th, in just a few hours, the iron line changed significantly in intensity, in width, in peak energy, symmetry, and in some of the observations, we see a strong iron K absorption edge at 7.1 keV, like the one here, and then in other observations, like here, there is no sign of it whatsoever. And you can also see, if you look at the spectra above 20 keV, that some of them have much more copious emission in the hard X-ray band, like here and here, compared to some of the other observations where it's pretty faint in the hard X-ray. So it's kind of interesting to see how the outbursts evolved over time. Now, fortunately for us, we can use this information, we can use the iron line shape to try and constrain the black hole mass, because when the disk is extended inwards all the way to ISCO for a black hole, the iron line becomes gravitationally distorted. So Paul Dragas at MIT is leading our relativistic reflection modeling, and he produced these snazzy plots to show how the mass varies as a function of different parameters. For some of the observations, it's very poorly constrained. We believe that that's because the disk was not extended all the way to ISCO for those observations. But for the others, our results do indicate that we're dealing with a black hole. So how does the discovery of a new black hole in the central parsec fit in with our view of the galactic center X-ray binary distribution? Now, back in 2018, we did a study of the X-ray point sources in the central few arc minutes of the galaxy. And we found that there are two distinct populations that you can see here. There are hard thermal sources, which we think are IPs, intermediate polars, which are roughly evenly distributed throughout the central few parsecs. And then we have some soft non-thermal sources, which are consistent with black hole LMXBs, and there are 12 of those. And all 12 of them are concentrated within the central parsec. So this was a really interesting result back then. And you can see here the spectra of these sources. The CVs have these strong iron lines. They're hot, they're thermal. The LMXBs are soft, they're non-thermal. They don't have these strong lines because these are quiescent LMXBs accreting at low rates. And so we published a follow-up study in 2021 analyzing the distributions of the different classes of X-ray transients in the galactic center. So in addition to the dozen quiescent black hole LMXBs, all of them concentrated in the central parsec that you can see highlighted in cyan in the image on the left here. We also, combining that with our analysis of the transients, which you can see plotted in the histogram here on the right, you can see that black holes are very strongly concentrated in the central parsec, while other compact objects are more uniformly distributed, as you can see in the histogram. So we currently have several papers out on the archive from this project that are undergoing journal review and in the pipeline, and our collaboration papers are listed here. You can scan the QR code if you like for a link to my monster multi-wavelength study. And there's more to come as well. We have a very rich data set that we've collected, and also serendipitously captured some other X-ray transients that outbursted nearby. So a lot of results coming out of this. So up until now, I've talked only about X-ray sources in the central arc minutes of the galaxy. But what happens when you zoom out and you look at the larger galactic center region? So Chandra has identified about 10,000 point sources. They're marked here. Sorry, the image is a bit blurry. They're marked with green dots here in the central 2 by 0.8 degrees of the galaxy. And for the most part, these sources have not been classified. And our research group has been studying the galactic center for a long time, and we've made a number of discoveries over the years so far. We've identified distinct populations of CVs And LMXB is distributed over different spatial areas and luminosity ranges, but we still don't know what the vast majority of X-ray sources in the galactic center are. For instance, how many of them are LMXBs versus CVs versus other sources, AGN, coronally active stars, and how are these different source classes distributed? And we're working to address these questions with two new groundbreaking surveys of the galactic center. These surveys were done by Gabriele Ponti with both XMM and Chandra, and they extend far beyond the scope of any previous galactic center survey. The XMM Heritage Survey covers the central 20 by 2 degrees of the galactic disk. You can see the exposure map in color here. And then there's the Chandra Legacy Survey. That's this area in pink right here. That covers the central 4 by 6 degrees of the galaxy, which is over an order of magnitude bigger in scale than the 2009 Lunar Survey, which was the previous major galactic center X-ray study. You can see that outlined in white over here. So to start with the XMM survey, we've already identified a distinct population of hard X-ray sources in the central degree in a region that's consistent with a nuclear stellar disk. This had never been seen in the X-rays before, that there's a distinct population within that region. So unlike the soft sources, which are more uniformly distributed throughout the galactic disk, there's a trend for the NSD sources to be much harder. And of course, the central molecular zone, the CMZ, has much higher absorption compared to the rest of the galactic plane, which raises the obvious question, are we seeing a harder population of sources in the center simply because the soft photons are getting absorbed in that region? And we believe that the answer is no, not just because the hard concentration doesn't fully align with the CMZ, which you can see here. It overlaps partially, but it doesn't quite line up. But also, if we assume a uniform population of sources, and we model the average NH at the full range of galactic longitudes, which we know from far infrared and radio observations, then we find that the resulting hardness ratios are not consistent with what we observe, meaning there has to be an intrinsic population difference in that central region. And looking a bit more closely at the distributions of the hard and the soft sources, in galactic latitude here on the right and longitude on the left, it's obvious that the hard sources are, which are red, the hard sources are red, the soft sources are blue, and the hard sources are much more concentrated towards the center. And I also overplotted in black a stellar mass density model that's scaled to fit both the hard and the soft sources. And as you can see, the SMD profile tracks well with the soft source distribution, but not the hard sources, which tells us that the hard sources are distributed much more steeply towards the galactic center than the stellar mass distribution. Now, what are these hard sources? We're still in the process of modeling, but I believe from what we know so far, that they are a group of very high temperature CVs, possibly because they have higher white dwarf masses than the CVs in the outer galactic plane, or possibly because they have a younger population of mass donors, which would also result in a higher accretion rate, of course, and therefore a higher temperature. Now, a quick note about the aforementioned Chandra survey of the central 4 by 6 degrees. We've developed a pipeline for processing these 350 observations, so be on the lookout for a new catalog in the next few months. We're working on that with Raphael and JSUB, and also Ian Evans is not here today. But this is another project that we have in the pipeline, and part of that survey overlaps with the XMM survey region as well, and so it would be good to be able to correlate those results. Now, before I wrap up, I just want to give a quick shout out to a few of the people who've contributed to the work that I've shown here today, including my advisors, Chuck Bailey and Kaya Mori. Some really talented undergrads have been assisting me, Ben, Eric, and Harry, Maxine Farah and Paul Dragis, who've done a lot of work on MAXI J1744. And of course, the CfA team that's been working with us on the Chandra survey, Jason, Raphael, Ian, thank you so much for all of your work. And Gabriella Ponti, who is the PI of the two major Galactic Center surveys that comprise the foundation of my thesis. To summarize, we finally have a new black hole transient in the central parsec after 9 long years. We have a huge multi-wavelength observing campaign that is still ongoing. We also have, on a much bigger scale, some new population studies in the Galactic Center region with these 2 new surveys, where we can see that the point sources are much harder in the nucleus tolerance region, which points to an intrinsically different population within that region. And finally, there's a new Galactic Center Chandra source catalog coming in the next few months. So look out for that. And that is all I have. So any questions, please hit me.
Great. We have questions. Yeah, please.
So I'm sort of millimeter wave astronomer, and I'm used to the maps of the molecular material. And the thing that surprises me is I don't really see any significant trace of the clumpiness of the molecular material in your map. Maybe I'm wrong about that, but I mean, there's a big dense cloud around Sgr A, and then between Sgr A and Sgr B2, there's not a lot.
So you mean here, or perhaps here, right? So let's see, I don't actually have Sgr A on this plot.
Well,
So this is Sgr B2, this shaded region right here.
Hmm.
I think it's a matter of scale. So you're thinking about clumpiness on a parsec scale?
well, no, 10 parsec scales. I mean, there's a big valley between Sgr B2 and Sgr A, right?
Yes.
Where the column densities are much lower. And you would think that you would see an indication of that. I don't know. I mean, I'm just saying.
So
this
I
may be
think,
interesting. I don't know.
yes, I think it's telling, because I think the hard X-ray sources aren't particularly susceptible to that kind of clumpiness, right? Because they just cut right through it. And again, the reason I don't think that I think that these are intrinsically hard sources, and it's not just that the soft component is getting absorbed, just because the weight that's concentration doesn't quite line up with those high density regions. So I'm not sure I would expect to see that kind of clumpiness for these sources. Certainly not the way it's been here, because here there have been to 100 sources per data point. If we look at an individual scale, perhaps, like where would Sgr B2, let's see.
What's it L of
Maybe-
about 0.442.
Yeah, so maybe around here. So maybe there is like a bit of it's kind of hard to see because it's so incredibly crowded. So there may be a bit of a deficit, certainly in softer sources within that region. But it's hard to see the structure from this plot right here.
Would also be interesting to normalize your X-ray sources by the stellar density at the same place.
Yeah,
Because
actually,
the inner parsec has got 10 to the 7 stars in the inner parsec,
yes.
and,
So,
and the surrounding areas don't.
right. So these are normalized just because I want to compare the shape of the distribution for the hard and the soft sources. But if you do look at the soft source distribution, you do see a kind of drop right about here, which I think this would line up with Sag B2, right?
Maybe, yeah.
Maybe, yeah. I have to actually overplot it on this figure. Yeah. Do you remember what it is in galactic latitude?
It's basically zero.
Yeah, so right around here. Where you see this dip over here, maybe.
So you know these sources and you say you want to classify them, great. What methods are you using?
So what I'm doing is I'm doing simulations, thousands of simulations of different classes of sources with different intrinsic spectral shapes, and also a wide range of absorptions at NH based on the observed values, and then trying to see how the resulting hardness ratios compare to the ones that we've observed here. So it's still in progress, and there are certainly some areas, if you're thinking about the phase diagram of NH versus intrinsic hardness, there's quite a bit of degeneracy, obviously. But there are some promising areas where I think we can isolate out and say, X percentage of the population in this part has to be this kind of source because nothing else fits.
Looking forward to it.
Me too.
Yes, please.
We'll start, Shifra. You mentioned something about getting the way work. Mass distribution, something for the hard sources.
Yes.
What can you say about the black hole mass distribution? And also from the, do you have constraints on this particular source?
So I think what I can confidently say at this point is that all the black hole candidates are very strongly concentrated towards the center. Within that group, I wouldn't feel comfortable saying we can say what the mass distribution is because the uncertainties are just so high. There are so far no dynamically confirmed black holes in the galactic center for obvious reasons. It's just extremely difficult to get those measurements. I'm actually working on another project, which we can talk about later, to do exactly that. But that's a ways down the road. Yeah, so we can only guesstimate really at this point.
So the overall spectral shape, because it's degenerate with absorption and accretion rate,
Yes, basically, there are just a lot of, there's degeneracies with respect to the source inclination, with respect to the inner edge, the inner radius of the accretion disk. You don't know if that's extending all the way to ISCO. It's degenerate also with the black hole spin, because obviously a spinning black hole will have a much smaller ISCO. So there are just too many variables that you can't exactly pin down to be able to constrain that at this time.
Okay, I will take Chair's privilege to ask one last quick question. You showed the hardness intensity diagram of MAXI J1744. And in a lot of the transient low mass exobinaries, we see a hysteresis pattern in this hardness intensity diagram. So first it rises and then it goes over. MAXI J1744 seems to be atypical, that it first goes to the soft state and then it went up and down. Do you have any speculation why?
So my speculation is, here, let me bring up the diagram. So my speculation is that we missed the part where it rose in the hard state to the fluxes that you see here. So basically what's missing here is the leg of the Q, right? This part right here.
Right, yeah, I guess I'm referring to it, it's here, which seems to be the soft state, then it goes up and then it goes down again and then over.
Yes, so it's maybe a matter of scale, but I think what I'm trying to say is that when it first outbursted, it was even fainter and even harder.
On there, okay.
So you're not seeing the whole picture, is what
Yeah.
I'm trying to say. And of course, Swift has a fairly limited band, so it's difficult to make out the full shape. Like you can see with NuSTAR, you really get the full diversity
Yeah.
of the hardness and intensity, and that's harder to do with Swift. But yeah, but again, like I said, I think there's like a whole thing missing here where it actually started really hard than burst. So.
All right, let's thank Shifra again. And the next seminar will be next week, so see you next week.
Thanks.